So this month's problem of the month is all about finding the distance between 2 points on a curve, specifically the curve that is a circle on the Earth, but those specifics don't really matter actually for the approach that I wanted to take. I remembered from Calc 2 there is a method to find the arc length, the distance on a curve, using calculus. I also knew that this was probably not the most efficient way to solve this problem. Um, but I want to go ahead and give it a shot. So how this formula works is if you have some parameterization of a curve, which looks something like this, so x is described with an input variable of t, which often represents time when you're in a real world context for it. And y is also a function of that same variable t. So x and y are changed together with respect to t. You can imagine that we're starting at t equals a, traveling along the curve until t equals b. And the formula for arc length then is the magnitude of the derivative. So if I take the derivative of each component, square them and add them together, this integral here will give me the length of the curve from that A to B. So I knew this formula existed, and it actually has a really nice extension to 3 dimensions. So if I have a 3-dimensional vector with z of t, then all I do is extend this. This is basically the distance formula. This is the distance formula to include z. And we still have dt there. So really nice extension into 3 dimensions. So knowing that I could find the length of a curve using this formula, I then just needed to figure out what could this be? And I thought, okay, well, even though it's 3 dimensions, it's still a circle. It shouldn't be that hard. It ended up being a lot harder than I expected, but we got there eventually. So the first thing I did was I thought about here what our graph looks like. So in here, I've got a nice visualization of the Earth. The blue lines are roughly latitude and longitude. That orange one is the prime meridian, and the equator is that red line. So here's my visualization of the Earth. And then we've got our 2 points in Oregon and in South Carolina. So you'll notice here I also have it connected through the origin, because any 2 points on the Earth can make what's called a great circle around the center of our Earth. So I thought to myself, how can I figure out what this equation of this circle would be? And my first instinct was recognizing that this sort of triangle here could be extended in all directions to be a plane. So I could just kind of slice the Earth with a straight line, like I showed in that orange video up higher on the problem of the month page. So with that being said, I asked myself, okay, how do I get the equation of a plane? Now that one I remembered from Calc 3, actually. So I said this is a skill involving Calc 2. I guess it kind of involves Calc 3. What I need in order to define a plane is I need what's called a normal vector. Basically, what is perpendicular to where I am slicing the Earth. Basically, the plane, I need a arrow that is 90 degrees off of that plane. So like how our XY plane runs down here, Z is perpendicular to X and Y. I'm trying to figure out just that same thing from this tilted plane. what's going to be a vector perpendicular to it. In order to figure that out, I also need to know where the points on the Earth are. And so I did that using spherical coordinates. I'm not going to get too into where those formulas come from for the sake of time, because there's already existing videos, and I'll link to that. But yeah, I'll link to this one. So if we look at this image here, we can see where our spherical coordinates come from, or in other words, what x, y, and z are for our points. So this variable here, rho, that represents the radius of the sphere we're on. So in this case, the radius of the Earth, the distance from the point to the origin. Theta is, like it shows here, the angle we've gone away from the x-axis. And phi is the angle we've come down from the z-axis. So using that information and the latitude and longitude, which gives us angles, we can get theta and phi from our latitude and longitude. I was able to get my points. So I will quickly go ahead and just show one of those. So here in Oregon, we had a latitude of 44 degrees. And we had a longitude of 124 degrees. So there are a couple things, one that's in degrees, and I want it to work in radians. So I did two things in figuring out what phi and theta were. So first, I did 90 degrees minus the latitude. So remember, phi is our angle down from z. Latitude is actually the angle up. So all I had to do was 90 degrees minus latitude to swap it from our angle up to our angle down. And then I multiplied by pi over 180 to convert to radians. So if I look at xy, if I were to go my 124 degrees, theta is going counterclockwise, so it'd put me over here somewhere. So I did negative so that I would move this way. And so that was really kind of arbitrary. Like, there's no labels on this sphere that I created. I just wanted the angle to move this way, clockwise. So I made it negative, and then again, I converted it to radians by multiplying by pi and dividing by 180. After I had my phi angle and my theta angle, and the radius of the Earth, which I used the radius in kilometers because NASA's answer was in kilometers and I didn't want to have to convert at the end. Then I had my rho, my theta, and my phi, and I could just use those formulas for spherical coordinates. And so I just plugged that information right into those coordinates to get my point. I repeated this process to figure out where the South Carolina point is. And then when I was trying to get that normal vector, what I did was I used the cross product, which is a way to generate an orthogonal, which is another word for normal, which is another word for 90-degree vector. So I took these two vectors, which are in the plane because they're pointing to the point from the origin, and I did a cross product, which gave me a vector pointing 90 degrees away from the two vectors in the plane. It got me this plane, which I was able to, in fact, get a circle by essentially taking my equation of the sphere and restricting it to the plane, which gave me a circle, which was great, and I was very excited, except that's not a parameterization, so it was kind of useless besides the fact that it looked pretty. So I kept thinking to myself, okay, I've got these coordinates of points, and they've got these two things. They've got two variables in it. Okay, how can I relate these two variables? We've got phi and we've got theta. How can I relate these two variables? And in Oregon, we've got a value for phi of about 0.788 and a value for theta of negative 2.165-ish. In South Carolina, I had a value for phi of about 0.994 and a value for theta of about negative 1.387. And I thought, okay, one way that I can relate two pairs of numbers is this looks a lot like having 2 points. And if I have 2 points, I can always make a line. So I went ahead and just used the normal line formula, y equals mx plus b. I found slope and my y-intercept, and I was able to create a relationship between theta and phi. And that relationship specifically can be seen here. I made theta be like my y and phi be like my x, essentially. And I got this relationship that theta would equal 3.7739t minus 5 point, I used t later, but this would have been phi. 5.13939. And even though I wrote rounded numbers here, I did use the full numbers when I was finding this equation of the line. I was just too lazy to write them just now. So I found this relationship and I decided, okay, we're going to call phi t. So wherever I saw in my spherical coordinates formula, wherever I saw phi, I replaced that with t, and wherever I saw theta, I replaced it with my new formula for theta. And so you can see that here in this formula, we've got cosine of phi is now cosine of t. Sine theta is now sine this function. And I was very excited about this. And immediately when I started looking at what this looks like, I thought, oh, that's a problem because it is starting here, and that is not on the circle at all. But if I let it keep going, it does go through those 2 points. And I thought to myself, well, I spent a lot of time getting to this point where I had this idea. Let's go ahead and try to get the arc length from this parameterization. Maybe it'll be close enough. And I used a whiteboard that I have, and I found the derivative. The derivative required some product rule because we've got products of functions, and a little bit of chain rule because we've got cosine of some stuff instead of just cosine of t. But it was already in radians, so I didn't have to worry about converting or doing anything weird with taking the derivative. And actually, the first time I tried this, I had it in degrees. And I didn't think about that until near the end, and I tried to do some converting, and I just didn't do a great job. So this round with radians was actually my second attempt, and it went much better. So after finding those derivatives, I went ahead and used an online integral calculator to figure out what the integral is. An important thing to be aware of when I was finding this integral was I needed to know what my bounds were going to be. So because I did a relationship between theta and phi, my lower bound was the phi that I started at. So the angle from the z-axis that gets me to Oregon. And then my upper bound was the angle phi that put me in South Carolina. And with all of this information, I was able to get an answer. And as expected, you can see on our visual here that this looks to be a little bit longer than the straight circle, and the answer I got was a little bit longer. It wasn't too far off though, so I thought to myself, maybe I should just stop there. I spent probably a couple more hours playing around trying to figure out how I would do a circle, and I really wasn't quite getting it. Couldn't quite figure it out. So I decided instead, okay, I'm gonna give it one more shot and I'm gonna look it up. So I looked up how to do it. And once I did that, I actually thought it made quite a bit of sense. So I'm gonna give you a quick overview of the concept of where the formula came from. So if I have a circle in XY, and again, I'm trying to do a parameterized curve, so I'm not just going to do x squared plus y squared equals r squared. I want to think about, okay, if I have a circle here, what are the coordinates of any point, right? And our coordinates, very similar, and in fact, part of the formula for spherical is what our x and y are going to be, right? So x, if this is our little angle theta, x is cosine of theta, and y is sine of theta. And that is just right up in the direction of our axes, which are perpendicular to each other. So if I want to find the equation of a circle in any axes, the first thing I need, I'm just going to redraw this. The first thing I need is two perpendicular lines in the plane that I'm working on. So if we look back here, the vectors that I used to create the plane are not perpendicular. So I had my vectors be the vectors pointing from the origin to the points that I know. The angle between them there is not 90 degrees. So what I needed to do is figure out, I needed to pick one of these vectors. It didn't matter which one. I went ahead and picked Oregon because that's where we start. I need to figure out a vector that is 90 degrees from this point. And we already had one that went along what I like to call the axis of the sphere that we're working with here. That was 90 degrees from our Oregon vector. So just like I did to find that one that was perpendicular, I took a cross product of these two vectors to get my other perpendicular vector. Once I have the two vectors that are perpendicular to each other, the coordinates actually work just the same. We just kind of have to tell it which direction. So this vector is vector A1, A2, A3. And this one is vector B1, B2, B3. Then I do that same circle where the one going in this direction is going to be cosine, the one going in this direction is going to be sine. And how do I tell it what direction that is? Well, I use A1, B1, and then A2, B2, A3, B3. So it looks like cosine of something in the direction of A1 plus sine of some angle in the direction of B1 as our x coordinate, times the radius, how far away we want to get. And then I repeat that same thing, cosine in the direction of A2 and sine in the direction of B2, and so on for that last coordinate. So that was how I finally got the parameterization of a circle through those 2 points. And now I go ahead and hide my first one. My second one here, you can see how it's acting kind of funky. It's because I have that red line and this new one that is right on top of it, which is what I wanted to have. So now a couple things. At 0, because I decided to start in Oregon, remember the vector I chose was pointing at Oregon, so 0 starts at Oregon. I needed to figure out, okay, when do I hit South Carolina? So now I've got my parameterization. Just like I did before, I need to find the derivative, which in this case was actually easy since I'm now adding things together. I don't have a chain rule anymore. So I just got to do the derivative of cosine and sine with some constant multipliers. But I needed to figure out, okay, where do I actually hit South Carolina? And you might notice that that should be whatever the angle is between the two of them. How I found that in this case was I just took my x coordinate and I set it equal to the x coordinate of South Carolina. And I used a calculator to solve for that. So the x coordinate of South Carolina was this number here. So I set 973 point something equal to my formula for x, and then I had a calculator solve for t for me because I didn't want to do it. And then I got, as you can see here, it's a number about 0.6. Finally, I have all the information to do the integral, and again, I used a calculator, and with all of that information, I was able to figure out that the distance is 4,011 kilometers, which was the answer that NASA got also. So, a successful calculus way to solve the problem. And another reason why I say this is an unnecessary, complicated way to do it is because once I have the angle between the two points, I can just use, in this case, since the angle is in radians, I would do a fraction over 2 pi times the circumference of the Earth, which is about 40,000 kilometers. And that would get me the same answer, no integral required. But I already come this far, so I had to do it the calculus way, see if it worked, and I did go get that answer.